discovery for the volume of a sphere. And I'm going to do it using related solids. I have a cylinder and a hemisphere. And in my model, I'm missing the other half of my sphere. But what I want you to notice is that the reason this is a related solid, let me just maybe I could just mark my spot with a pencil very quickly. So the sphere ends there, right? If I turn it around and do that, you can see that the entire sphere would have essentially the same height as this cylinder, okay? So it stands as tall as the cylinder, and when I place this sphere on top of it, its great circle, the largest circle that fits inside of that sphere, is a perfect fit with the cylinder, so they have equal radii, the sphere and the cylinder. So I want you to keep that in mind, okay? So in theory, I should be able to slip that hemisphere down in there so it sits snugly inside of there, and I should really be able to push the sphere all the way to the bottom. But can we just agree that if this sphere has the same height as this cylinder and the same distance across as the cylinder, that the cylinder takes up more room than the sphere in terms of their volumes? This volume is going to be greater, okay? If they stand the same number of units tall and the distance across each is equivalent, this has to hold more than that. We know the volume formula for the cylinder. We're going to tweak it to come up with a volume formula for the sphere. So let me just do it with water quickly to show you the relationship. You're not going to be able to see the angle initially, but I'm just going to do this really quick, and then I'll move my camera briefly to show you. So I have a hemisphere. I'm going to pour it into the cylinder. It doesn't fill it, nor would we expect to fill it. We've already said that we know the cylinder is larger. So I'll slit the camera down very quickly. So what do you think? I say it looks like more than half, but I don't know. Is it 3/4? Is it 2/3? So what I can do is, let's see if we can fit another hemisphere in there. Is it gonna spill over the top, or is it gonna leave room yet at the top? Okay, how many does it take? So here comes my third hemisphere, and that did the trick. Okay, so just showing you that 3 hemispheres filled the whole thing. That meant that 2 hemispheres filled 2/3 of our cylinder. Okay, so we have seen informally that this is going to take up 2/3 of the same space that this does. So let's deal with our cylinder for a second. I know that the volume formula is pi r squared times its height. Pi r squared, that all seems to relate perfectly to a sphere, right? But when you talk about height, we don't really generally say that a sphere has height. We either talk about its radius or its diameter. And the diameter is what we're thinking of when we think of these heights or distances being equivalent. Okay, so how many radii does it take to make a diameter? A radius plus a radius equals d. So instead of calling this h, I'm going to rename the height of this cylinder. This cylinder stands 1 diameter or 2 radii high. Okay, so we're going to substitute that. So the volume of this cylinder is the area of its base times its height times 2r. So this particular cylinder has a volume of 2 times pi r squared times r to the 3rd. Okay, so now this sphere does not have an equal volume. This sphere is less. It's a fraction of this. And what did we decide? This sphere is 2/3 of that volume. So to get the volume for this sphere, it's 2/3 of means that we're multiplying, of 2 pi times r cubed. Well, that's all over 1. And if we multiply the 2's in our numerator, we end up with 4/3 pi r cubed over 1. So this formula just simplifies to 4/3 pi r cubed. And that is the volume formula for a sphere.